All right, so let's get started. So today, what I'm gonna do is just kind of review what you've already learned in the class. So if by chance you want to go back and do some reviewing, rehear the lecture, I'm going to give pretty much the exact same lecture, except for I'm going to go through this at a slightly faster pace. This is the second time around. So just kind of going over it again. And once again, if you want to review it, you can fast forward it to the type of reaction in which you want to focus on. So what we said is that basically there are billions of different types of chemical reactions out there. And we said it's impossible for us to kind of commit to memory all the different products that can be produced from all these different chemical reactions. So we said in order to make this process easier, that chemists actually came up with ways in which you could categorize the chemical reaction. Now, in this class, we are only going to focus on 5 different types of chemical reactions. We're going to look at the combination reaction, which once again, it is sometimes referred to as a synthesis reaction as well. You'll typically hear me refer to it as just a combination reaction. We'll take a look at the decomposition reaction, the combustion reaction, the single displacement reaction, the double displacement reaction, both the acid-base double displacement reaction, and we'll also look at the precipitation double displacement reaction. So moving forward into the notes. The first reaction that we're going to look at is going to be our combination reaction. And if you look at the definition, it simply says a reaction that involves a combination of 2 or more reactants to form one product. And that's why when you look at it, basically we have this generic equation that simply says that I've got A and B, which are my reactants, and they're coming together to produce one product. So a combination reaction, you will always take the reactants, and regardless of how many of the reactants you have, they'll come together to produce the products. Now, keep in mind, for the combination reactions that we'll be looking at in this class, we are strictly going to be looking at A and B as being elements. So if we look at it, what we're really going to be seeing here, and once again, it's not just the A plus the B, we're going to really be looking at it from the standpoint of an element plus an element coming together to produce a compound. And when it comes to the states of the elements, that's just based on your knowledge of the periodic table. And we've talked about the periodic table already. And we've talked about all the different states of the elements. If you need to, go back and review it, but it is something that I expect for you to know at this point. As far as the compounds, one of the things that I will tell you now, and I'll just write it in here really quickly, is it says in the notes, which I'll show you in a second, it says that if the compound happens to be an ionic compound, that the state is going to end up being a solid. Because if you remember, we learned from the previous chapter that ionic compounds produce crystalline solids. If it happens to be a molecular compound, remember, a molecular compound is made up of 2 or more nonmetals. If it's a molecular compound, then we put right here that Mr. H is going to have to provide me with the state. Because one of the things that we talked about with these molecular compounds is we said that some molecular compounds exist as solids, some exist as gas, and some are liquid. And I cannot expect you to know the state of every single molecular compound. Ionic compounds, easy, because we said that ionic compounds would exist as crystalline solids, so you should just know it's going to be a solid. So when we look at these examples that I have down here, the very first thing you want to do is you want to acknowledge the fact that, hey, magnesium is a metal and nitride is a nonmetal. So therefore, what I'm going to do is I'm going to go to the periodic table and figure out what the charge of magnesium is going to be. And when you look at the periodic table, you'll see that magnesium is a 2+ charge. And then when you look at the periodic table for the nitrogen as an anion, it would be nitride, which is N3-. And the only thing I'm going to do is I'm going to put this together to produce an electrically neutral compound, just like you learned how to do in the previous chapters. So what we're going to do is I'm going to see the least common multiple is going to be 6. So that means I need, in this case, 3 of the magnesiums, and I need 2 of the nitrogens. And at this point, I have just predicted what the products are going to be for these two elements when they come together. Now, of course, I've got to go in here and indicate the states. I know that metals are all going to be solids except for mercury, which happens to be a liquid. Nitrogen, well, that's a gas. We said that, hey, ionic compounds are going to be crystalline solids, so I know your state as well. And then it's just going through and balancing this. So I'm going to go through this pretty quickly because you should know how to balance the reactions, since we already learned that. And here we go. We're finished with that first problem. For the second problem, we've got calcium. I'd run to the periodic table, figure out that calcium is a 2+ charge. Oxide, well, that would be a 2- charge. So once again, as far as the compounds, I'm putting this together strictly based upon charges. 2 + 2-, they will cancel out, and I'll get CaO. And I have now figured out what the products are going to be here. Only thing I got to do now is just, once again, go back, indicate the states. You're a metal, you're a solid. Oxygen, you're a gas. You're an ionic compound, so you're going to be a crystalline solid. And then just go through here and balance it. I'll put a 2 here and a 2 right here. For the next problem, I'm doing the same thing. I'm going to take calcium, which is a metal, so I'm going to go in here and say, okay, calcium, based upon the periodic table, we already said you're a 2+ charge. Chloride, based upon the periodic table, you're a -1 charge. So when I put this together, I'm going to end up with now 2 of the chlorides needed in order to cancel out the calcium's charge. So now I get rid of these ions here, since I figured out what the compound's going to be. Go over here, you're a metal, so you're a solid, you're a gas, and then once again, you're ionic compound, so you're a crystalline solid. And then if you look at it, it's already balanced. Now, one thing I want to point out about this particular reaction is I want to make sure that we are clear, crystal clear, that if you have a diatomic, so I've got a diatomic right here, it only has to be a diatomic when it is sitting by itself as an element. Inside of a compound, it can have any subscript it needs. Now, it looks as though in this product over here for the calcium chloride that it's staying a diatomic, but remember, the only reason I had 2 of the chlorides is because I needed 2 of them to cancel that charge out. So that's by sheer coincidence. You'll notice over here for the oxygen, 2 didn't stick over there because calcium was a 2+ and oxide was a 2-. So once again, I'm putting things together strictly based upon charges. And once again, the diatomics will only be a diatomic when they are found by themselves. All right, so let's go through a couple more problems here. For the next one, I've got iron. And iron is a type 2 cation. So if you run to the periodic table, you're not going to find its charge there. But over here in the parentheses, I do tell you that in this case, I want the iron to be a 3+ charge. So iron 3+. Oxide 2-. Least common multiple between the two is 6. So I want to have 2 of the Fe's and 3 of the oxide, so the charges will cancel out. So that's going to give me Fe2O3. You're a crystalline solid, you're a solid, you're a gas, and then once again, balancing this out, I'm going to put a 2 here, a 3 here, and then I am going to go and put a 4 in front of the iron. And now this is balanced. 2 more for the combination reactions, and then we'll be done with combinations. Aluminum. Well, you're a type 1 metal, so I know your charge, you're Al3+. And let's do this. Move this down just a little bit out the way. And then when we look at the oxide, you're O2-. So put it together, Al2O3. Once again, least common multiple is 6. You're a solid, you're a gas, you're a crystalline solid. And then once again, it's balancing this out. I'm going to go with a 3 here, a 2 here, and a 4 right here. All right, last problem. For this problem, basically what I have is I've got a non-metal and a non-metal. One of the things you have to remember is that when it comes to these non-metals, that they do not have charges when they form molecular compounds. There are no ions in molecular compounds. And because there are no ions, I have no way of figuring out what the products are going to be. I can't use ions to cancel out here. So if it's a molecular compound that's being produced, then I'm going to have to tell you exactly what molecular compound is being produced. And I'm telling you right here by providing you with the name. And also remember, I told you for molecular compounds, I would also tell you what the state was going to be because they occur in multiple states. They're not like the ionic compounds that are just crystalline solids. So in this case, it says tetraphosphorus, so that's 4 of the phosphorus. Decaoxide, well, that's 10 of the oxygens. It's telling me verbatim right here that it's a solid. So the only thing I gotta do if I have 2 nonmetals coming together is really just write down the formula, whatever it tells me to write down, and then really just go back in here, indicate the states. You're a solid, you're a gas. Go through, balance this out. It looks like I'm gonna put a 5 here, and I'm gonna put a 4 right here, and now it's gonna be balanced. All right, so that is the crux of a combination reaction. We're taking 2 elements, we're sticking them together based upon charges. And once again, trying to make sure those charges cancel out if it's producing an ionic compound. If it's a molecular compound, we just write down its formula based upon the name that's actually being provided here. So don't forget, 2 elements coming together to produce that compound. All right, next reaction we'll look at is going to be our decomposition reaction. Now, decomposition reaction, if you look at it, it's like just the opposite of the combination reaction. If we go back up here and look at it, combination A plus B yields AB. Decomposition, AB now breaks apart to produce A plus B. And if you think about decomposition or to decompose, if we have some, I don't know, animal that's decomposing, that means that it started off as being an individual animal, and now it's starting to break apart into these smaller pieces. And that's the same thing that's taking place with this decomposition reaction. They're decomposing. We're starting off with a compound. The AB is a compound. And then it's breaking apart into now smaller pieces, the A plus the B. Now, one of the things to keep in mind is that when it comes to these decomposition reactions of starting off with a compound, that these compounds are not going to just magically just break apart. They're just not going to sit there and say, hey, I'm breaking apart. Instead, what has to happen is there has to be some energy or heat that's causing these compounds to break apart. So normally it's going to require some energy or some sort of heat. Now that energy could come in the form of electricity, or the energy could come in the form of something such as heat. To give you an example, in your notes, and for some reason I don't have them here in these notes that I must have downloaded my older notes, but pretty close to the notes that you have. In your notes, you'll see that you have H2O, in this case as a liquid. And then you'll have an arrow going over top of it, and then you'll have electricity over top of the arrow, and then it's going to say it produces H plus H2 plus O2. And in order to get this water to break apart, you do have to put electricity into it. It's not going to, once again, water is not going to spontaneously just break apart. But we have to put energy into it. So for these decomposition reactions, one of the things that we'll be looking for is just keep in the back of your mind that you do need energy or you need heat for them to fall apart. So the first type of decomposition reaction we're going to look at are just going to be these binary compounds. Binary compounds just mean that they don't have any polyatomic ions in them. And the type of compounds that we'll be looking at, since we're going to only be starting off with just the compound, I'm going to tell you now that it's going to be a, let's help you out here. It's going to be a compound, once again, on this side of the arrow, on the reactant side. And what I'm going to do is I'm going to tell you the states. If it's an ionic compound, then we said it's going to be a solid. If it's a molecular compound, then it's going to be Mr. H. So I'm going to have to tell you the state of some molecular compound. And because it's a binary compounds that we're looking at, these are going to break apart into an element plus an element. So that is what it's going to break apart into. So if you look at it, this looks verbatim to this one here, except for it's flipped around. So the combination reaction versus the decomposition, it's just the two are just flipped around in this case. So we're going to look at, once again, just binary compounds. And if you have a binary compound, then the only thing you have to do is just break it apart and show the two elements it's going to actually produce. So the example I give you is example number one is you got sodium chloride. And with sodium chloride, if you provide it with either heat or electricity, and really truthful, the sodium chloride, to get it to break apart, you're not responsible for knowing this, you do have to put electricity through it. And what would happen is it breaks apart into the two elements. So we get sodium, and also we get the diatomic chlorine being produced. So for me, I feel like the decompositions are a little bit easier because I'm not putting anything together based upon charge. The only thing I've got to do is just go into these and just write their elements. So for instance, where I see the water here, what I would do is I would write down H plus O. But remember, one of the things I told you is go back, look at the NiH rule, because you got to know whether or not this is a diatomic. And remember, if you use the NiH, you'll find out that hydrogen is a diatomic. So it's got to be a subscript 2 there. Oxygen also falls under the NiH rule. So therefore, it's a diatomic as well. And then I'm home free. For water, we'll put a liquid here. For hydrogen, it's going to be a gas, and then it's just going in here and balancing this one out. So if I look at it, I need a 2 here and also a 2 right here. And I'm done. For the next one, I've got NH3, which is ammonia. And for this one, I would just, once again, break it apart and show the elements. Here goes nitrogen. Here goes hydrogen. Once again, use the NiH rule, check and see if they're diatomics, those elements. And in this case, nitrogen happens to be, and hydrogen as well. Hydrogen I know is a gas. Nitrogen I also know is a gas. Now, for ammonia, this one I should have told you to state, because I told you for molecular compounds, I'm providing you the states. So here, this is going to be a gas, but if this was a problem that was on your worksheet or on the test, I would have already in that parentheses a G sitting there. So you wouldn't be expected to know that state. Then if we look at it, going through and balancing, I'm going to put a 2 here. I'm going to put a 3 right here, and I'm finished. For the next compound, I've got, in this case, the two elements being Fe, plus I've got Cl. Fe is not a diatomic, it's a monatomic element. It can sit by itself. But the Cl, which is chlorine, is a diatomic. You're a gas, you're a solid, you're an ionic compound, you're a solid. And it looks like I need to balance this out by putting a 2 here, a 2 here, and a 3 right here. For the next one, I've got just phosphorus being produced and also oxygen being produced. For this one, if I look at it, I'm just going to go in here and I'm going to do the following. I'm going to say, okay, let's see. Phosphorus, you are a monatomic element. Oxygen, you're a diatomic element. Phosphorus, you're a solid. Oxygen, you're a gas. And this compound over here, oh, I did it again. I'd have to tell you that this molecular compound in this case happens to be a solid. So I'd have to provide you the state of that molecular compound. And then if we look at it, just balancing it out, it looks like I need a 2 here, a 4 right here, and a 3 here. So that's it. So molecular, when we look at these compounds, these binary compounds, just break them apart into the elements. Hardest part is really just using the NiH rule to kind of figure out whether or not the element is going to sit by itself or whether it's going to sit as a diatomic. Now, one of the things that we said is that there's also 2 special decomposition reactions. And if you remember, we said that these 2 are just ones that you really kind of have to commit to memory. So there is no like rhyme or reason for, well, there is a rhyme or reason for why it's occurring, but for this class, you just have to kind of commit to memory what's actually taking place. And basically the 2 special decomposition reactions that we're going to look at is we're going to look at if we have a metal carbonate, and this is their metal carbonate right here, or if we have a metal hydrogen carbonate going through a decomposition reaction. Now, in order for these decomposition reactions to actually occur, you do need to supply heat. So these require heat in order for them to proceed. Now, if you look at it, I'm telling you now that if you have a metal carbonate and it is being heated, that it is going to produce a metal oxide. And that's why you see the M there and also the O. So there goes my metal oxide. Keep in mind that that metal oxide is being put together based upon charges. So I'm still going to use my charges. So use charges to, let's see, we can go here to make the compound. I guess could have said to put together the compound. It would have been better, but we got it here now. And then the CO2, you're just going to write that down. This just produces CO2 as the other product. So if you look at the first example we have here, we got calcium carbonate. Once again, it's an ionic compound, so it's a crystalline solid. And then for the metal, in this case, the metal was calcium, so that was a 2+. The oxide was O2-, so therefore it went together as a 1-to-1 here. It's an ionic compound, so it's a solid as well. And then CO2, you're just putting down. And in this case, CO2 happens to be a gas. So really for this sort of problem, where it takes the, I guess, most amount of effort, is really just figuring out what that ionic compound's formula is going to be based upon using your actual charges. So for instance, if we look at the next one, we've got sodium carbonate. And in this case, it's going to produce the metal oxide. So I'll use my metal of sodium +1, oxide, which is 2-. And then I'm going to simply put these together based upon charges. So it would be Na2O. And once again, that's an ionic compound, so that's a solid. And then the other product is just going to be CO2 and gas. So once again, that product I'm just writing down. That's just from memorization of this actual reaction. Okay, 1 second. We're changing in between classes, and they're using this festive Christmas music here. All right, and I'm back. So if we look at it, at this point, you'll notice that it is now balanced. I got 2 sodiums, 2 sodiums. I got 1 carbon, 1 carbon, 3 oxygens, 3 oxygens. So I didn't have to do anything with that one. For the next one, let's see what we got here. I've got a metal carbonate, so I know it's going to produce the metal oxide and also carbon dioxide gas. So even if you wanted to, you could go in here and say, hey, you know what, if this was a test, I already know what one of the products is going to be. I'm going to write down CO2 gas so I can pick up at least some partial credit there. Now, of course, you still got to go in here and figure out what that metal oxide is going to be. So I know the metal is going to be Fe. In this case, the oxide I know is O2-. Now, you do have to figure out what the Fe's charge is going to be, but we've already learned that because we learned that if I wanted to name this compound, I would have to figure out what the Fe's charge is going to be. And if you remember, we said we can use our anion, and the analogy of the anion, that carbonate is a 2-. I've got 3 of them here, so that means that collectively all the carbonates are 6-. That means that the Fe's over here collectively have to be 6+, but I want the charge of just one of Fe's, so I'm going to divide it by the 2, and that gives me 3+. So now I know that the Fe is a 3+ charge. And now, once again, find a least common multiple. I can go through here and say, that's going to be 6, so I need 2 of the Fe's. And I need 3 of the oxygens. You're an ionic compound, so therefore you're a crystalline solid. And then once again, it's just now going in here and balancing this reaction out. I see 2 Fe's, 2 Fe's. One of the things I do see is I see right here, I got 3 carbons. So I'm going to put a 3 in front of the CO2. Now I've got, in this case, 9 oxygens. I've got 3 on the product side plus 6. That gives me my 9, and this thing is now balanced out. All right. Next special decomposition reaction is going to be if we have a metal hydrogen carbonate. And this one is very similar to the metal carbonate. If you look at it, the product will be a metal oxide, just like we saw in the metal carbonate. You'll get a product of carbon dioxide, just like you got in the last one. The only difference between this one and the metal carbonate is the metal hydrogen carbonate produces just one more thing I have to write down, which is H2O. But if you look at it, it's still the only thing you have to do that requires work is, once again, just putting together this compound, the metal oxide, based upon its actual charges. Give me 1 second. Let me finish this up. And I'm sorry, I had somebody at the door who was trying to come in, and they're stepping away now. All right, here we go. So if you look at it, for this particular one, what we're going to do is we're going to go in here and we're going to look at sodium. We're going to say, sodium, you are a +1. And then oxide, you are a 2-. So therefore, when I look at the actual formula, the formula is going to be Na2O. And then for the other products, I'm just going to write down CO2 plus, I'm going to write down H2O. And for this one, I can clearly see that, once again, you're on a compound, you're a solid, you're a gas. And in this case, the water is going to come off as a vapor. And the reason why is because we're actually using that heat. And we heat this thing up, it's at a very high temperature, and it's at such a high temperature that the water is above its actual boiling point, and it just comes off as a vapor. To balance this, if we look at it, I just need to put a 2 right here. Let's see, a 2 right here. And let's see, we got here 2 sodiums, 2 sodiums. I got 2 hydrogens, I got 2 hydrogens. I got 2 carbons, so let's put a 2 right here. And then with the oxygens, I got 6 oxygens. I got 4, 5, and I got 6. It's balanced. For the last one, I'm going to go in here once again. I'm going to say, okay, I'm going to get my metal oxide. So Fe is going to end up being a 3+ charge here. And the oxide is an O2-. So once again, least common multiple will be 6. So I get Fe2O3. So Fe2O3 as a solid. Also, I'm going to get my CO2 gas. And hold on 1 second while the music finishes up. All right, and I'm back. And then also, it's going to end up producing the water vapor. And then once again, just going in here and balance this out. I see that I have 2 Fe's. So let's put a 2 right here. In this case, I've got a grand total of 3 hydrogens times a 2, which is 6 hydrogens. So I'm going to go ahead and put a 3 right here. For the carbons, if we look at the carbons, I've got a grand total of the same thing. I've got 3 carbons, and then I got times 2, so that's going to be 6. So I'll put a 6 right here. And then for the oxygens, if you look at it, I've got 3 times 3, which is 9, times 2, which is 18. And let's see what we got here. We got 12 right here, plus we got another 3 right here, so that's going to give me 15, plus we got 3 right here, so that gives me my 18, and it looks as though we are now officially balanced here. All right, here we go. So just remember, for the decomposition reaction, if you have a compound that's sitting on the reactant side and it's by itself, if it's a binary compound, then you're going to simply go ahead and break it into its 2 elements, and be mindful of the fact that you got to figure out whether they're diatomics. It's easy. Nothing's being put together. You're not using any charge. Just write the elements down. If it happens to be a compound that's on the reactant side and it's a metal carbonate, then once again, you got to put that metal oxide together based on charge and just write down CO2 and balance it. If it's the metal hydrogen carbonate, then it's the metal oxide, carbon dioxide, and water vapor that's also being produced in this case. All right, on to the next reaction. The next reaction we have here is going to be our combustion reaction. And combustion simply means to react with oxygen. That's what it means. Anytime I have oxygen sitting on the reactant, so by definition, it happens to be a combustion reaction. So if we look at it, when I say something such as, hey, the wood is combusting, then it is a factual statement because the wood is burning in the presence of oxygen. And if the oxygen was not there and we suppress the oxygen, the wood would no longer combust and it would no longer burn. So the first sort of reaction to look at is this magnesium reacting with the oxygen. And the only reason I'm pointing this one out to you is that if you look at this one, I have an element plus an element coming to produce a compound. This is also classified as a combination reaction. However, it can also be classified as a combustion reaction because I do have oxygen as one of the reactants. Now I'm going to tell you, if this was a problem that was actually on the test, I would expect for you to see it more as a combination. Hey, it's two elements. I got it. I'll put it together based upon charge and I'll be done with it. But if you call it a combustion reaction, that is perfectly fine because technically it is a combustion reaction as well. The combustion reactions that we're really going to focus on is we're going to focus on what are called hydrocarbon combustion reactions. And let's make sure that we're clear with what a hydrocarbon is going to be. And if you look at it, it tells us that a hydrocarbon is simply going to be a compound that is made up of carbons and hydrogens, and sometimes it's also going to have oxygen in it. So if you look right down here, I give you the basic backbone of a hydrocarbon. I simply say CXHY, where X can be any variable you want, Y can be any variable you want as well. So long as I have some carbon with some hydrogen, it is a hydrocarbon. Right here, we have CXHYOZ. Same thing. I don't care what the X, Y, and Z happen to be as far as their numbers. Any combination of numbers you put there, by definition, these two things are going to be referred to as our hydrocarbons. So those are the basic structures of hydrocarbon. Now, one of the things that we're going to see is that when it comes to hydrocarbons, when hydrocarbons react with oxygen, what they're going to end up producing is they're going to end up producing carbon dioxide gas. Water we'll see is going to come off as a vapor. And also we're going to produce a tremendous amount of heat. That's why, hey, we burn wood, we know wood is going to produce heat. Combustion reactions have a tendency of producing heat. So if you look at it, basically what I did here is I gave you the basic backbone of what's going to happen for a combustion reaction. If I have CXHY reacting with O2 gas, it's going to produce CO2 gas plus H2O gas, plus we're going to get this heat that's coming off of it. If it happens to involve a oxygen inside of that hydrocarbon as well, you're still getting the exact same product, CO2 plus H2O plus delta. When it comes to combustion reactions, these are by far the easiest reactions to work with, because as soon as you see a hydrocarbon plus oxygen, the only thing you have to do is write down CO2 gas plus H2O as a vapor, plus we get our heat coming off of this as well. Oxygen, of course, is a gas, and really, to tell you the truth, the hardest part of combustion reactions is just balancing the reactions. That's where you're putting effort in, because the CO2 plus H2O, you're just going to have to commit that to memory. Hydrocarbon reacting with oxygen, CO2 plus H2O, plus to give it some heat off. So if I balance this, I see 8 carbons. I'll put an 8 right here. I got 8 hydrogens, so I'll put 4 times 2 is 8. Next, I got 16 oxygens right here. Plus, I got 4 more oxygen. That's going to give me a grand total of 20. So I'll put a 10 right here. And now this reaction is balanced. For the next one, I've got C4H10. Now, this is called butane. It's the same butane that you'll find in a cigarette lighter. And if you give that cigarette lighter a small spark, then the butane will react with the oxygen, and what you're going to end up producing is you'll produce CO2 gas plus H2O gas, plus you'll produce delta right here again. And once again, this is going to be the heat that's coming off in the flame, in the form of flame, from that butane cigarette lighter. And then once again, just balance the reaction out. 4 carbons, 4 carbons. 10 hydrogens, I'll put a 5 here, and that gives me 10 hydrogens. For this one, I've got oxygen-wise, I got 8 plus 5, that's 13. Don't forget our special trick that I taught you. I told you that if you have something such as a odd number, and I have to try to fix it with the oxygen, that you just take that odd number of 13 and place it over 2. And one of the things we said is we can't leave this way. We have to go back and multiply everything by 2 to get rid of that fraction of 13 over 2, which means we get 2C4H10 gas plus 13 O2 as a gas plus 8 CO2 as a gas plus 10 H2Os plus I get my delta here. And now it's balanced. For the next reaction, I see a hydrocarbon plus oxygen. So I'm going to really quickly just write down here CO2 gas plus H2O gas plus delta. Oxygen happens to be a gas. If I balance this out, it looks like I got 6 carbons, 12 hydrogens, so put a 6 here. And this one you have to be a little careful with. Because this one has oxygens also in the hydrocarbon, I can see that I've got 6 oxygens right here. I also have 6 oxygens sitting right here. So that's kind of a wash. So what I need to account for is really the 12 oxygens that's sitting here. So I'll put a 6 right here in order to balance this reaction out. Now, this particular reaction that you're looking at is actually C6H12O6 is known as glucose. And that glucose is reacting with oxygen. If you remember in class, I told you this is nothing more than a respiration reaction that you'll learn in AP biology. You do not have to tell me it's a respiration reaction in my class. You just tell me it's a combustion reaction. But one of the nice things about this is that if you look at this particular combustion reaction of this glucose and oxygen, you'll notice that the human body, which we burn glucose, we breathe in oxygen, we exhale carbon dioxide and also water, and also our body produces heat. Our body is just like a cigarette lighter. It goes based upon pretty much the exact same reaction. Even if you think about an automobile burns octane. Octane, when it reacts with oxygen, produces CO2 plus H2O. So the way in which our human body actually produces energy is very similar to the way in which energy is produced for our automobile or for our cigarette lighters, or even if you look at it, if we take something like the natural gas that you have at your house that you use to heat your house. Well, natural gas is made of methane. Methane reacts with oxygen. It produces, in this case, CO2 as a gas. Also, it produces H2O as a vapor. And then also it produces all that heat that you use to heat your house or use to actually cook your food. Now to balance this one, since I already got it here, might as well balance it. It looks like I got one carbon. I got 4 hydrogens, put a 2 right here. That gives me a grand total of 4 oxygens, put a 2 right here. And now this is balanced out. All right, so that is our combustion reaction.